So the next workspace on our list is the Simulation Workspace. So if we go into Simulation, first thing that pops up is it asks you what study you want to do. Now in Fusion 360 we have a load of different options of what simulations we can do. Between static, modal, electronics, which we haven't even covered in any of these videos, but we can do electronics and then discuss how they're going to be cooled. Other thermal properties such as increasing the heat and seeing how it distributes throughout a part. Buckling, thermal stress, nonlinear static stress, event simulation, and shape optimization. These are all options of things you can do to try and determine what might go wrong with your part. Now, simulation is a really, really important part of any design and make process. You want to make sure that you do some virtual testing before you go out and manufacture it. Otherwise, you could end up making it, realizing something is terribly wrong, and then having to rebuy all of those materials and remake it all again, when you could have just done a virtual simulation in a very short amount of time. In this video, we're going to go through a static stress simulation. So we're going to select static stress and create a study. The ribbon, again, completely different. We have a load of different options in this ribbon, and you'll see on the left that we have a study 1 static stress. You can create as many studies as you want, and they'll come up on the left-hand side as different studies. So this means that you can do lots of different tests with different forces or different constraints, or even different simulations altogether, and still keep all of the results from all of them. As with anything else in Fusion, we work left to right, so we're going to start, after creating our study, with the Simplify option. By clicking on Simplify, it opens up a limited menu of design items so that we can change our design and make sure that it's exactly how we want for our simulation. In this, we are going to simulate one of our linkages on one of our legs. Just make sure that it's strong enough to support everything by putting a load on it. What that means is that we only need to do something on this one leg. But having all of these other parts in our simulation, if we don't remove them, they would still have to compute what's happening in that simulation. And even though nothing would happen because it would be constrained and there'd be a load, it'd be very difficult to see what's going on. So it's much, much easier if you simplify your model down to exactly what you need. It'll save time on the simulation because it won't have to compute so much, and it'll make sure you get the results that you want. This is what the main part of the Simplify menu is. On top of that, it allows you to take certain geometries that might be very complex and simplify them slightly to make them slightly more geometrical, simple. That way your simulation will still give fairly accurate results, but without taking a long time to compute. In this case, we just want to remove all of our parts other than one of these linkages. Now the way you can do this is you can select the linkage, right-click on it in your browser, and select Remove. Now in this case, we want everything to be gone apart from this one linkage, so you can actually use the Remove All Except Selected option. If you click that, everything will be removed from your design, apart from what's been selected. And you'll see down at the bottom a timeline will appear, and all of these remove operations will appear. So if you ever want to go back and change that Simplify, you can go back and it has its own specific timeline. Something to be aware is that just hiding an item from a simulation isn't going to remove it from the simulation. Fusion will give you a pop-up to say there are some hidden parts, so you need to make sure that you remove them and not just hide them. This is all we need to do for our Simplify, so I'm going to finish the Simplify. Next across we have materials. Now we've gone along, we've applied quite a few materials at this time, so I'm going to go and check the study materials. This is the only part, but if there were multiple, they'd all come up in this table. And we can see that currently it's plastic, we have it as ABS, that's the component that we're using, and it's the same as what's in the model at the moment. It's ABS, that's what we want, that's what we're going to be using, and that's what the model was selected. But for some of them, you might not have remembered to change your physical material, or you might have just changed the appearance, like I think we did with the dome, for example. And there, what you can go in and do is change, either go back to the design menu and change the physical material there. If you're going to do multiple studies, that can be a bit easier. Or if you're just doing one, you can actually go in and select from the long list of materials that you can use. Here, we're happy with it being the same as the model, which is ABS plastic. So I'm going to click OK. The next thing we have to do is constraints. Now a constraint effectively locks in a part of your model. Otherwise, if we put a load on it and there's no constraint, all that it would compute is that the part would be pushed away rather than necessarily bending. there needs to be a fixed item on your part in order to determine what the forces are doing to that. And in our simulation, or in real life at least, that part would be fixed to our servo block. But because that's not here, we need to add this constraint to say that this certain part or this bolt connector will be fixed. Now we're actually just going to use a structural constraint, which is C on your keyboard. And we're going to constrain this top hole here because we know that this is fixed to the servo block, so it wouldn't move. Instead of selecting the edge, we want to actually select the surface on the inside because we want that whole surface to not move because it's all connecting to the fixing. You can change which axes are fixed and you can change the type of fix that it is. So you could have a pin or frictionless. In this case, we're going to leave it as fixed just because we want to see the bending of this part. Click OK, and you'll see the little lock appears on your model. Next, we want to apply a load. So we've now fixed one end, and we want to see how much our load of our hex pod is going to bend this lathe. So therefore, we're going to apply our load to the other end. If you click on load, again, there are lots of different types of load. We're just going to add a standard structural load. There are lots of different types within the structural load. We're just going to add a standard force. We're going to put it on the inside surface area of this hole. Once you have, we can rotate this around so it's facing down. Because currently it's only facing up, and all of our forces are actually going to be facing down. So you just have to rotate this around a little bit until you're happy with it facing downwards. 180 degrees. You might have to rotate it a few times depending on what axes it came in as. I'm just going to make sure this is facing straight down. Perfect. And this will put the whole force on this entire surface area selected. Once we've done this, we can apply our load either here, the magnitude, or over in the right on the box. I'm going to make this a 10 Newton force. So it's 10 newtons pulling down on this part. Once you're done, click OK. And you'll see that that load is applied. You can still just about see it in there. And you can apply multiple different loads and multiple constraints to a part. Now in our case, we only need one of each. But if you have a slightly more complex part that's say fixed in two places, or might have different loads in different places, you can apply as many as you'd like. The next part is contacts. What contacts are when you have multiple components that are going to be interacting with each other. It defines the tolerance between them and how they interact. Now in this case, we don't need that at all because we only have one component, so there's nothing to interact with. So I'm just going to leave this completely. But you might want to generate automatic contacts with a certain tolerance, just so that any interacting components can be included in the simulation. Finally, you can toggle the mesh, and it will generate a mesh. We're not going to do this now because it will automatically generate when you solve. But if it's already been solved, you can look at the mesh, or you can look at the degrees of freedom view. This will help you determine what in your model needs to be fixed fully, or what is free. We've applied this constraint, so we know that it's fixed fully on this end, and we're happy. But if it's only partially fixed, or potentially fixed, or if it's just free to move completely, this will ruin your simulation and not necessarily give you the result that you want. So this is a really easy way to see what's happening in each of your components. Now again, we only have one component in this study, so it's fairly easy to tell. But as soon as you have lots of different components interacting with each other, this can be a really useful tool. In Manage, you can change some of the information. We're going to leave this for now. But the main part is this solve section. You have what's called the pre-check. If you click on the pre-check, it'll come up and tell you how the software thinks that your performance has been on this simulation. It's basically grading you on setting up your simulation. If there's a green tick here, or it says it's happy, then it'll give you the green tick, and that means that before you even simulate your part, it thinks that it's probably going to have a good chance of giving good results, or at least a result, and not failing. It's a really useful tool, especially if you're using up cloud credits, because it means you don't have to spend your cloud credits on something that's clearly not going to work. It's just a really quick check before. Always try and make sure that this is green. Once you're happy and you're ready for your simulation, you can click Solve. It'll bring up this box and you can choose to do it on the cloud or locally. I'm just going to do mine locally because it's a really small part. You could do it on the cloud if you have a really complex part to stop putting strain on your computer. Click on Solve, and you'll see that it comes up with a job status. This is our part, this is the study, and this is the status. You can also see this in your job status up at the top. Because I'm solving locally, it won't let me close this, whereas if you're doing it on the cloud, you can close it, let it run in the background, and it will let you get on with doing other simulations. Now we can see here that the first thing that pops up is some results details, and it's telling me that I have a safety factor of 4.66, which is very good, and there's a big green tick here, so it looks good. If this falls below a certain level, you can see you have a graph down here. It was just hidden behind my face, but here you go, here's the graph. If it's above 6, it'll become blue, and it'll tell you that it's over-engineered, i.e. the part that you have is too strong, you don't need it to be as strong as it is, so you can potentially reduce its size or its thickness and have less material wastage. If it's in green, that means that you're in a good place, that's above 3. Between 1 and 3 it's potentially okay, but you might want to review it and check it, it's getting a bit close. And if it's between 1 and 0, it means that it thinks that your safety factor is too low and there's a high chance that it will fail. I'm going to close this, and you can see that our simulation has generated a graphical image. What this is doing is it's showing you how much your part has deformed, and you can adjust how much it's scaled to. In this case, it looks like it's deformed a lot, but it really hasn't, and that's because it's adjusted by a certain amount to give you a visual representation. You can choose actual to see how much it's actually going to deform, or you could choose undeformed if you just want to not see that at all. I'm going to leave it on adjusted just so you can see what's happening. Once you close this, you can actually look at a lot of other information from down here. In this case, we're choosing low case 1, which is the only one we have, but you have a long list of different things that you can look at. Currently, we're looking at the safety factor, which we saw was 4.6, but here we can actually look at the stress, and we can see that the highest stress point is where it's coloured in up at the top with this top hole. That's where it's most stressed. You can use this to potentially change your model depending on what you might need. So you could give this a larger hole or a wider fixing at the top and not the bottom if you needed to change things. We can also look at displacement. As you'd expect, the very end is the part that's displacing the most because it's furthest away from the pivot. We also have reaction force and strain. If I go back to displacement, you can actually animate this. If you go into results, you can animate, choose play, animation, and you'll see the movement, how it's deformed. You can type in or check on two-way, and it will just keep looping between two. And you can change the number of steps that it does. If I add this to 100, you can see it's going a little bit more slowly, but in a lot more detail. As I said before, you can change between your deformations. So looking here, this is the actual deformation. It's not actually moving that much. And you can see that on displacement and on your stress, it gives you an actual value. And we can see that it's only going to deform by 0.37 millimeters, which really isn't that much. So it's really not too much of a worry. You can display your mesh. You can compare to a different simulation if you've done multiple. And it allows you to inspect different parts. So for example, I could inspect with the inspect tool, I could show the minimum max, or I could create a surface probe or point probe. This allows me to select a surface, and it'll tell me how much that surface is deformed or how much stress that has. I could see, for example, at this hole, it's actually only deforming 0.3 millimeters. So if there's a certain tolerance on your bolt that you need, this can be a really useful tool to look at. There are a couple of other things that you can look at and ways that you can look at it. You can also generate a report. If you click on this, it'll generate a report with all your information that you can save and potentially give out to somebody else. Once you're done, you can finish results, come back and generate another study. But that's a rundown of the Simulation Workspace. There are a load of other simulations that you can do, whether it's thermal or electronics cooling or an event simulation. There are lots of different simulations you can do to test different parts of your design. This is the one we're going to do for now, but I'd recommend taking a look. If you click on study, you can click on each and see exactly what those do, have a short description. So it's a very useful tool. That sums up the Simulation Workspace. After this, we're going to go into the manufacturer and briefly cover what you can use the manufacturer for.